Okay, nerds, let's get started. Alright, so we did a video already that covered the beginning portion of this. Okay, so we should have this first part done, and now we're moving into energy. Okay, so this is going to kind of parallel what we've been doing with SPDF orbitals. Okay, so let's go through this really quick. After Bohr proposed the solar system model that electrons orbit a nucleus just like planets, he called the orbitals energy levels. Considering the following Bohr models of a boron atom. Okay, so we're looking at a boron. We have our protons, which we have 3 of. We have 2 neutrons, so our mass is 5. And we have 3 electrons. Okay, we have 2 in our first shell, and we have 1 in our outer shell. Okay, so we know higher energy levels are further from the nucleus. For an electron to go into a higher energy level, it must gain more energy. Okay, so an electron, to go to a higher energy, it must gain energy. Sometimes the electron can absorb light energy. Recall that different colors of light have different frequencies and wavelengths. That's what we discussed up here with our previous video. If the right color, and therefore frequency of light, is absorbed, then the electron gets enough energy to go to a higher energy level. The amount of energy, which we symbolize with E, and the frequency, F, of light required related by the following equation. Energy equals H times F. Okay? E, energy, is the energy measured in joules. Okay, so just like we have distance measured in feet, okay, we have energy measured in joules. And our frequency is measured in hertz, which we talked about previously. And then there's also H, which is Planck's constant. Okay, so this is just always a number. Okay, and Planck's constant we measure in joules per hertz, which is the same as a joule second. Okay, Planck's constant is 6.63 times 10 to the negative 34th joule second. Okay, so we have that highlighted. Now we're going to move on to the back, and we're going to do some problems. But not yet. First, we're going to continue reading. An electron that absorbs energy and goes to a higher energy level is said to be excited. Okay, so for absorbing energy, we are excited. And we move to a higher energy level. Let's go ahead, let's draw that really quickly. So at the very top here, we're going to draw that. Make sure you have this on here. So we're going to draw our first shell. We have one of our electrons, and if it jumps up to a higher shell, okay, we're going to absorb energy. And this is what is said to be excited. Okay? If an excited electron loses energy, it will give off light. The frequency and color of light depend on how much energy is released. Again, the frequency and energy are related to the above equation. Okay, that above equation is H times F equals energy. Okay, frequency and energy are related by the above equation. When an excited electron loses energy, we say that it returns to its grounded state. Since not all electrons start out in the first energy level isn't always an electron's ground state. Okay, so let's draw this second one. We have our first shell. We have our second shell. We can even have a third shell. Yeah, let's go ahead. Let's draw a third shell. So anytime if we have an electron, okay, and it moves further down, if it moves back in, okay, in doing so, okay, it releases light, which we call a photon. Okay, so every time we can see light, that's electrons moving, not going out, but going in. As an electron moves in, energy is released. Okay, we're losing energy, and we have an energy, it's returning to the ground state. Returning to the ground state. In doing so, we give off light. Okay, depending on where it's jumping to, so how far down and in, okay, and how many energy levels it's moving, that's going to change our frequency and our color. Okay, so we're going to do a few problems on this. Okay, so first off, does an electron need to absorb energy or give off energy to go from the second to the first energy level? Okay, so if we're going to the second to the first, second to the first, we're doing what's over here. Okay, we are losing energy. Make sure you answer this in a full sentence. Okay. Next one, how is it possible for an electron to go from the third to the fourth energy level? Okay, so if we're moving from the third to the fourth, we're absorbing energy and we're becoming excited. A good example of this is running electricity through something, or setting something on fire, or providing energy to it. So if we give anything energy, it's going to absorb that energy and our electrons are going to move out. Okay, once we stop giving that energy, they like to quickly move back into the inner shells. All right, so now let's do some math. Okay, so number 10, red light has a frequency of 4.37 times 10 to the 14th hertz. It's required to excite a certain electron. What energy did the electron gain from the light? Okay, so we're using the equation energy equals Planck's constant times frequency. Okay, so we want to know our energy. Place a box around energy. Okay, so to set this up, we need Planck's constant h times F. Planck's constant is, on the back, 6.63 times 10 to the 34th. Negative 34th. And let me zoom in so you guys can see that a little bit better. Joule second. Okay. We're going to draw our little box just like we did last time. And we want to multiply that by our frequency. Okay, so we're going to times that by our new number. And our frequency is 4.37 times 10 to the 14th hertz, which we will also write as a number per 1 second. Okay, so now we have to see what cancels out in this problem. Okay, so what we're looking for is what's on the top and what's also on the bottom. Okay, so if we're looking here, seconds cancels out, and we're left with joules. So that's what our answer is going to be in. Okay, we always measure energy in joules, so we know we set the problem up correctly. Okay, so with our trusty dusty calculators, we take 6.63 exponent negative 34. Okay, type that in, and then we multiply it by 4.37 exponent 14. Okay, if you need to rewind and watch me do that again, make sure you see what you get. Hit equals and see what you get. Okay, we should get 2.897 times 10 to the negative 19th. Okay, we're going to round it to 2 decimal points. So when we round it, 2.89, we look at the 7. The 7 says that this goes up. 9 becomes 10, which means this goes over, we raise this by 1, so we're 2.90. So answer here is 2.90 times 10 to the negative 19th. If we leave this blank, I'm going to write tacos behind there, and that's wrong. We have to write joules, J. 2.90 times 10 to the 19th joules. Okay? That's our first problem. Let's try out number 11. So 11, the energy difference between the first and second energy levels is a certain atom is 5.01 times 10 to the negative 19th joules. Okay, so this is our energy. Our energy is this. Underline those. What's our frequency? So now we're looking for frequency of light necessary to excite an electron in its first energy level. Okay, so now that we're looking for frequency, we have to rewrite our equation. Okay, so this is where we do our triangle. Energy, Planck's constant, F. If we're looking for energy, okay, it's H times F. If we're looking for frequency, it's energy divided by Planck's constant. If we're looking for Planck's constant, it's energy divided by our frequency. Right now we're looking for frequency, so we're going to take our energy and we want to divide it by Planck's constant. Okay? So to solve for frequency, it should equal, we're going to rewrite it over here. Frequency equals, make sure you don't write too far off to the side because we are going to glue this paper down. Frequency equals energy divided by h. Okay, so let's set this problem up. First number we have is energy. 5.01 times 10 to the negative 19th joules. Okay? And we want to divide it by h. H is going to go at the bottom, 6.63. So now that we're doing division, it goes on the bottom. This number divided by 6.63 times 10 to the negative 34th joule seconds. Okay? In doing so, we got to see what cancels out. J cancels out. One on top, one on the bottom. We're left with seconds. Okay? And we can always have, we're going to have a number per second, which is what we measure frequency in, or hertz. Same thing, let's type this in. We have 5.01 exponent to the negative 19th. And now we're dividing it by 6.63 exponent negative 34. Now we get 7.556 times 10 to the 14th. So if we round this correctly, 7.55. Our next number, 6, tells us to round up, 7.56. .56 times 10 to the 14th. And we are left with seconds, but our answer's up here per second, so this is the same thing as per 1 second, okay? Or another way of writing that is 7.56 times 10 to the 14th hertz, Hz. And then you put a box around it. Okay? All right, let's move on to 12 and 13. What is the frequency of light given off by an electron that loses this many joules? So here's our energy. What is our frequency? Okay? Set it up just like the last problem. Okay? So for here, we're going to do the same thing. Frequency equals energy divided by h. Okay? Set it up, make your box. 4.05 times 10 to the negative 19th joules. Same thing, we're going to divide it by Planck's constant. So we're dividing it by 6.63 times 10 to the negative 34th. Go ahead, plug it in and see what we got. Okay. B, what wavelength of light does this correspond with? Hint, use C equals frequency times wavelength. Okay? So now, when we solve for this problem, let's go ahead and solve it. 4.05 exponent negative 19 divided by 6.63 exponent negative 34. Okay? We end up getting 6.11, because we're going to round it. 108, so 8 makes this a 1, times 10 to the 14th. And this is in joule seconds. So our J's cancel out again. And we're looking for frequency. This is in hertz. Okay, or 1 per second. Okay, so now we have our frequency. We also know C. Okay, C from the other side, okay, was 6.63 times 10 to the negative 34th. I'm sorry, that is Planck's constant. C, from the other side, if we take a look, is 3.00 times 10 to the 8th. That's C, or the speed of light, meters per second. So now we're looking for wavelength. We want to know what wavelength is. Okay? So same thing as we did last time. Wavelength equals, from what we did last time, if we're solving for wavelength, speed of light divided by frequency. So now this equals C divided by F. Okay? So we set up our box. Speed of light is 3.00 times 10 to the 8th meters per 1 second. And we're going to divide that by our frequency from our last problem. So now we're dividing that by 6.11 times 10 to the 14th. And that's per 1 second. Okay? So now seconds cancel out, and we're left with meters. And that's what we measure wavelength in, lambda. So 3.00 exponent 8. We're going to divide that by 6.11 exponent 14. We get 4.909, or 4.91 times 10 to the negative 7th. Unit that we're left with is meters. Okay. 13 and 14. Do atoms of different elements have different numbers of electrons? Answer that here. Number 14. If all the electrons in an atom A are excited and then lose their energy and return to the ground state, okay, so we're returning to the ground state, so our electrons are moving in. Will we let off, same electrons will let off a combination of frequencies and colors of lights. Each frequency and color corresponds to a specific electron, making a transition from an excited state to a ground state. Considering an atom from element B, okay, would you expect the excited electron to let off the exact same colors of light as atom A? Why or why not? Okay? Go ahead, use your EdPuzzle questions to help you answer that here and give a little summary.